So today I'm going to be talking about some work that I've been doing with a number of excellent collaborators on trying to sharpen the connection between real-world QCD, in particular at collider experiments, with its underlying field theory description. And so particularly when it comes to phenomena such as confinement or QCD flux tubes, there's often a kind of big gap between what is done in the theory world and what is done in experiments. And so what we wanted to do was to try and sharpen this connection. And I hope to be able to convince you that due to a lot of recent advances, it's now possible to actually study on the experimental side observables which are much more closely connected to what one is interested in from the theory side. And this makes me optimistic that we can actually learn things about confinement phenomena in the real world from experiment. So as everyone here is very familiar, in the last several decades, there's been tremendous progress in our understanding of gauge theories, which has been driven both by amazing numerical simulations as well as by insights from a variety of simplified toy theories. And so this has led to a qualitative and in certain cases quantitative understanding of many simplified observables. So things like expectation values of Wilson loops, certain correlation functions, et cetera, et cetera. But sharpening this picture for real-world QCD and relating it to observables of interest in real-world QCD remains an extraordinary challenge. But as you've heard at this meeting, there's been a lot of exciting progress from this collaboration. And so at least for myself, so one of the most beautiful aspects of real-world QCD is that it is in fact real. And so this is also what makes a lot of the goals of this collaboration very important. And so one of the nice opportunities that we have, because QCD is real, is that much like in condensed matter, we can in principle try and study some of its phenomena experimentally. And just like in condensed matter, we can hope to be kind of inspired on the theory side by what we observe experimentally. But of course, in reality, this is much more complicated because of the time scales which are involved. And so one of the major difficulties, which is important to appreciate, in trying to learn things from experiment about real-world QCD is not just that real-world QCD is a very complicated field theory, but it's actually that a lot of the observables that we have access to experimentally are very complicated observables. So for example, very complicated collisions like this. And so if we could actually go out and measure, for example, some correlation function or some kind of Wilson loop expectation value, even if we couldn't understand it from first principles calculations, we could at least compare it to similar observables which we understand in our favorite toy theories, and this would provide a lot of insight into phenomena that we don't understand in QCD, and then we could try and improve and kind of sharpen our understanding of these interesting phenomena. And so this is really one of the major difficulties in this field. And so what we would like to try and do is to kind of sharpen this relation between what we can actually observe experimentally and things that we can understand kind of very sharply, at least in toy theories, to try and draw general conclusions. And so because of this kind of lack of connection, in the last several decades, I really think that this is what has kind of driven experiment and theory apart, particularly when it comes to QCD. And so this kind of idea of trying to connect theory and experiment and collider physics experiments has a very, very long history, going back now about 50 years to the kind of beginning of QCD. And so I wanted to highlight at the beginning that because this fall is actually the 50th anniversary of some of the first attempts in trying to connect theory and experiment in QCD. And so in particular, in 1975, a little bit after the introduction of asymptotic freedom, George Sturman, who was inspired by kind of what you actually do in experiments, introduced what we now call the energy flux operator. And so this is motivated by what you literally do in an experiment. And so we wanted to define an operator which is just like a calorimeter cell, and it's kind of measuring the flux which comes off in some particular direction. And so what he proposed is that one could measure, or one could compute, expectations values of that energy flux operator, which, as I'll show in a second, are kind of related, or are directly related to 3-point functions in the underlying theory. And so what he showed also in his early work is that this expectation value of this energy flux at some particular angle is actually calculable in perturbation theory. And so this is very important because unlike things, let's say like scattering amplitudes, this object actually has a smooth infrared limit. And so this is something which you can directly measure in real-world QCD, and it can actually tell you something about the dynamics, for example, of confinement. And so this idea was significantly generalized in the kind of late 1970s by Stephen Ellis and collaborators, who said one can measure just like you do, for example, in the CMB, instead of measuring kind of multi-point correlation functions of temperature fluctuations, you can do this also for these multi-point correlation functions of energy flow. And so in particular, he proposed that you could kind of characterize events in QCD by measuring multi-point correlation functions, which again, in the underlying field theory, would correspond to like 4, 5, or higher point functions in QCD. And then this would tell us a lot about the distribution of energy in QCD and ultimately of the underlying field theory. And so this was something which was pursued vigorously in the kind of late 1970s, going on to the late 1980s. And it was very important for establishing the theory of QCD as the theory of the strong interactions. But then as that was kind of established, people lost interest in this kind of direction, and these things were kind of left for a long time, about 30 years, as just kind of something which people do in QCD, and nothing kind of beyond that. And so these observables were resurrected about 30 years later in this important paper by Hoffman and Maldacena. And so they really emphasize kind of two important key things. So the first is that these observables, which I'll refer to as energy correlators, are kind of interesting observables for characterizing generic quantum field theories. So they're not something that you just do in QCD. And in fact, they're very natural in, for example, conformal field theories, where you don't necessarily have a standard S matrix. And you can consider an example. And so this picture was made by David Simmons-Duffin. And so his favorite conformal field theory is the Ising model. And so you can imagine that you have some 2 plus 1D sample of the Ising model. And you can excite it at some particular location, and then kind of measure the fluxes which come out to infinity. And so this is some natural set of observables which you can measure in just completely generic theories, much like you do in QCD. And so this is very helpful in trying to connect what people do in the specific case of QCD with what you can do in more generic quantum field theories. The other very important thing, which it was already kind of known, but they really re-emphasized in this work, is that you can directly relate what you're actually measuring, or what you're measuring in infinity, to operators, in particular local operators, of your underlying field theory. So in the simplest case, if I'm just interested in measuring, for example, the energy flux at infinity, I can write down this calorimeter cell, which earlier I showed this picture of George Sturman had written in terms of the action on kind of particles coming off to infinity. But you can really write it as a particular integral of the stress tensor of your underlying theory. So you kind of dot it into some particular direction, take it off to infinity, and so if all the particles in your theory are massless, you really just integrate it along future null infinity. And so this provided a nice kind of connection between what these detector operators and the kind of local operators of your underlying theory. And so this was extremely important because it really provided a direct relation between what you can do in experiments, namely measuring these asymptotic fluxes, and the kind of spectrum of local operators of your theory. And so instead of being functions of the kind of positions of these operator insertions like you would have for a normal correlation function, so instead of being just functions of position, these are now functions of angles on the celestial sphere. And so I'll often denote these angles. So instead of doing it in terms of the literal angle, I'll often write it in terms of this variable z, which is just related to the angle like this. And so in particular, z goes to 0 as these two detectors become on top of each other, and z goes to 1 as these two detectors become antipodally separated. Yeah. Good, absolutely. So yes, I'll be more careful about this later. And so of course, in real world QCD, we are measuring massive particles, and this has an important distinction. And so the way that I've written this shown here as its actual limit can be done properly to incorporate the fact that in QCD things have masses. And I'll actually show this, of course, as you would expect, has an actual impact on the distribution, and I'll be more careful about that later on. But in the case that it is a CFT, it really reduces to this very simple integral along null infinity. And so often I'll kind of draw that schematically, but I'll highlight this later when we do it in real world QCD. Perfect. OK. And so this kind of had two very nice impacts on the field. So the first is that just at a practical level, it enables us to use properties of these local correlation functions to compute observables which we can measure in collider physics experiments. So just from a purely practical perspective, this is extremely useful, and often these are much better understood than what we might be trying to do in collider physics experiments. And so the second thing, which is in some sense much more important, is it made us able to connect to calculations in our favorite toy theory. So this is a perfectly well-defined observable. You can take whatever theory you want, and you can compute it. And so this really provided a very nice connection between what we want to do in the real world, or observables that we can study in the real world, and observables that we can study in simplified theories. Okay. And so the other thing, which I've already emphasized, but I just want to make very clear, is that we can actually directly measure these observables in the particular case of electron-positron colliders. So here we have a literal map between what we would like to do in this kind of picture and what we can actually do in experiment. And so in particular, in this case, we can really excite the QCD vacuum with a local operator, which is just the electromagnetic or the electroweak current, and we can measure the asymptotic fluxes which are coming off to infinity. And in particular, we can do that as a function of the angle between the particles, and so we can really map out the behavior of this correlation function over its complete kinematic range. Going all the way from this kind of back-to-back limit, which I mentioned, all the way to the limit where the detectors are so-called collinear or on top of each other. And so this is extremely satisfying because this really provides a very sharp relation between what we can do in experiment and where we can literally study QCD and 4-point functions in particular of the stress tensor. And so it should be clear that one is under no illusion that we cannot really understand this non-perturbatively in real-world QCD, and we're very familiar that there's huge distinctions between the complexities of QCD and the complexities of these toy theories, but just establishing such a mapping is a good first step towards understanding this. And so this really enables us to identify observables where we can go and then compute them in other toy theories and then try and sharply understand distinctions in particular related to confinement in the real world. And so, of course, this was an observable which was proposed very early on. And so people measured it at very early experiments. And so I wanted to just, since I've been highlighting some of the experimental aspects, to kind of show this measurement. And this will also familiarize you with what you're going to be seeing later. So this observable was first measured actually in 1979, so a very long time ago, at the Pluto experiment. So this is when experiments were quite small. And so this is running at 13 GeV, so it's quite a low energy. And so they made this plot of the distribution of this energy correlator observable. And so again, just to kind of orient you, so it always ranges an angle between 0 and 180 degrees, going from this regime where you have the two detectors literally back to back. You have some kind of middle region where your detectors that are at kind of 90 degrees. And then you have this limit where the two detectors are collinear. And so you get this nice kind of distribution which comes out. And so because I emphasized that this was something that is really calculable in QCD, you should be able to directly compute this and compare with what you get in real world or in the data. And so this was done very early on. And there was actually a huge amount of kind of theoretical firepower which went into trying to make this first kind of theory data comparison. So in particular, it was computed in this limit of the kind of two detectors coming back to back by Parisi and collaborators. And so the reason why there's kind of specialized calculations for the different limits I'll come back to. It was then computed by Konishi and Veneziano in this small angle or collinear limit. And then it was combined with this calculation, which I mentioned earlier, by Ellis and collaborators in the middle. And so what you can see is that you have quite horrible agreement between the theory and the data. But nevertheless, this was kind of a first attempt at actually making a comparison between descriptions of energy flux and correlations in QCD and trying to learn something about QCD by comparing it with this type of observables. And of course, this is not unexpected because this is at very low energies. OK. Sorry? So this is E plus E minus. So this is actually the center of mass energy. It's high compared to the QCD scale. And so I should say, so it is high, but it's not that high. And so you have quite large non-perturbative corrections. And so I should also emphasize, so this is done with like leading order calculations. So from a modern perspective, we can get much better agreement. And I'll show later, so we can now go very much better. But for this level of calculation, it is not a bad agreement. And so exactly related to your question, one thing which will become very important in going forward is to understand the scales which are actually probed by the measurement of this correlation function. And so in particular, we're very used to for correlation function, or for example, Euclidean correlation functions, that the scale which is being probed is just essentially proportional to the inverse of the distance between the two operators. And so as you bring the operators together, you probe the UV, and as you bring the operators apart, you probe the IR. And so because these observables or the detectors are placed at infinity, you essentially flip this relation. And so this is actually very nice, or this can be viewed as advantageous, because the scale that you're probing is actually dependent on the angle between the two detectors. And if they're at some generic angle, just for example 90 degrees, where z is generic, you're really probing the scale at q squared, which is related to your question. But as you bring the detectors together, as z becomes small, you actually probe the infrared of your theory, and you're probing a scale q squared times z. So this is why in these experiments you're actually probing also much smaller angles. And similarly, as you bring the detectors exactly back to back, you're probing a scale of q squared times 1 minus z. And so one of the reasons why this is very nice is it's just like as if you actually had a correlation function of the local operators, and you can kind of dial their positions and probe this theory at different scales. And so in particular, if you have just a single collider at some high scale q squared, then by varying the angle between the two detectors, you can actually sweep out the energy that you're probing the theory at over, for example, multiple orders of magnitude. And so in particular, if you had, for example, infinite angular resolution, you could really perform this measurement all the way from a kind of very high scale q squared, where you're probing the dynamics of the kind of partons in your underlying theory, and you can sweep this to sufficiently low angles that you actually have kind of sub-confinement resolution, and you can kind of really image the transition from partons to hadrons. And so this is this nice advantage of doing things asymptotically, is you can kind of really, in one experiment, sweep out a kind of huge range of scales in QCD. And so this is very nice, because we now have both an observable where we can actually understand what it's probing in the theory, and we can also use it to study the kind of confinement transition, or to sweep out the dynamics of QCD as a function of scale. And so this was attempted early on, and I'll explain these plots in more detail later for the actual measurement, but this is similar to the measurement which I showed as Pluto, where it's measured as a function of the angle between the two detectors. But this is now done at the higher energies of LEP, so this is now at a center of mass energy of about 90 GeV. And you can see that what happens, so what we said that we wanted to do to study, for example, the dynamics of confinement, was to study these two asymptotic limits, either when the detectors become perfectly on top of each other, which is this side, or as the detectors become very back-to-back, which is on this side. And you can see in the data that essentially what happens in those limits is things just go completely crazy, and so you kind of lose control over what's happening in your experiment. And so as a result, these were kind of the best measurements which were ever performed, and they were performed in essentially the late 90s. And there's been no kind of experiments since then. And so as a result, the kind of direct measurement of this confining transition, where you could really kind of use this to learn something about confinement in QCD, was kind of always left murky and was never really performed. And so this is kind of problematic or a bit disappointing, because of course, as you know, LEP is now retired. And so in particular, you can go to CERN, and this is a particular detector from the LEP experiment. In particular, this is the Delphi detector, and so you can read some plaques about how nice this experiment was. And you can also get this book, which has this preface by Rolf Hauer, who is the director of CERN, where it says the kind of LEP experiments have published their last papers, but it will live on in textbooks. And so this is a little bit disappointing for trying to actually study these kind of nice properties of confinement. And so actually, I kind of attended a number of the early workshops of the Simons collaboration on confinement and QCD strings. And so we were really motivated to kind of go back and actually use this data, because of the recent interest in confinement, to really kind of bring it back to life and try and focus on understanding aspects of confinement in these energy correlator observables. And so this will be a little bit of a detour, but it's kind of an entertaining detour on trying to actually go back and resurrect the data from these early LEP experiments to use it to have improved insight into confinement. And so as I said, motivated by this recent interest in confinement, with my collaborator, Yanji Li, who is a very good, serious experimentalist, he wanted to go back and actually try and use this early data to study confinement. And so one thing which is very nice is that two of these experiments, Aleph and Delphi, actually invested significantly in data preservation. So they stored all their data that was taken at that time. But of course, there's a very different thing to just having some of this data and using it for example, educational purposes, versus trying to actually do kind of precision physics with this. And so Yanji really started this program to kind of resurrect this data to be able to do precision physics, and in particular study aspects of QCD using all this beautiful data. And so one of the reasons why this is still actually possible is that these collaborations still exist in some very reduced format. And so you can go, for example, to CERN, and you'll find this room where they actually have, for example, some remaining Aleph members. And if you go into it, you'll actually find, so at that time, they had event displays apparently printed on transparencies. And you'll find this actually just fused into the wood of the table. And so this suggested that there was going to be a big gap between really trying to extract this data and using it for modern purposes. So as one continued, things got even worse. And so in particular, one thing which I had not appreciated is that all this old data, of course, they don't use kind of modern computers, but is all stored on very old floppy disks. And so in particular, you actually need to find the original computers to be able to run this. And so even after that was actually done, some of these had even just kind of dumber problems, namely that some of them are password protected. And so you have some of these very old Windows computers where you actually cannot extract or run, in particular, certain of the detector simulations. And so this really took an immense amount of effort from these experimentalists. A lot of it is just not even physics, but just kind of detector work in going through kind of old notebooks from this time to kind of extract all this data and get into a form which is manageable. And so the outcome of this is after this huge amount of effort, which took several years, we actually have the kind of fully modernized versions of the Aleph and Delphi data sets, which we can use to study aspects of QCD. Yes? So, good. So far it's only been done for LEP1. So there is the data for LEP2, but it has not yet been analyzed because this is a little bit more complicated because you go above the WW threshold. And so this needs to be treated a little bit more carefully. But the data is there, it just has not been reanalyzed. And this is in particular an issue because for some of these detector simulations, so there's one experiment, so this one is password protected, and so you actually can't do the detector simulations, and that prevents doing more sophisticated things. For this Delphi experiment, you actually do have the higher energy data, and that's being analyzed right now, which will be very nice. Yes. Yes.
Can't you like crack the passwords? Is it really old?
Yeah. So yes. So I think that will be done, but that has not been done yet. Yes. But yeah. It's outside the scope of this talk. Yes. But yes, I mean yes. And so that would be very nice because then that would enable the full LEP2 data set. And so you'll see that I'll only have things at the Z pole, and so the LEP2 would be very nice to go even higher energy, and that is underway currently. And so the kind of outcome of this is there's now this nice group of experimentalists from quite a few different universities, which go to the name of this E+E- Alliance, which are really kind of serious experimentalists trying to use this data. And so kind of another fun anecdote is that this entire LEP1 data set, so the LEP2 one is bigger, but the LEP1, which I'll use here, is 28 gigabytes. And so for like $8, you can have your own copy of this and can easily analyze it very nicely. Okay, so one question which you should ultimately have about trying to do something better with this old data is that these measurements, for example, of these energy correlators are going to be fundamentally limited by the detector resolution. And so this is something which is famous in cosmology, that to really kind of get these beautiful pictures that one sees, one had to really update from the kind of COBE to WMAP to Planck. And so a question one should ask is if we have these kind of very old and outdated cameras, how can we do better without having a new detector? And so to understand this, it's a bit of a technical detour, but I kind of wanted to emphasize it because it's really what enabled these measurements to give a lot more kind of power than they used to. So one thing which is important to know is that charged particles, which leave tracks, can be measured with very, very good resolution, in particular using tracking detectors. So you can think of them as being able to be measured with these kind of very modern detectors. Whereas neutral particles are what are measured by these giant detectors out here, and these have very poor resolution. And so in all these old calculations, and in particular the statement of George Sturman, which I cited before, require that you sum over both the charged and the neutral particles. And so this is because of this KLN theorem, which really requires that you sum over all states to achieve an infrared finite answer, which is computable in perturbation theory. However, in the kind of 30 or so years since these early measurements, there's been a lot of progress in our understanding, in particular, of effective field theory. And so using kind of modern effective field theory and renormalization group techniques, we can actually do something for these detectors, which is very much similar to what we normally do in the study of local operators. Namely, we can just use kind of matching calculations, and to match between UV detectors and infrared detectors, which measure the hadrons. And so in particular, you can think of these infrared detectors as actually literally measuring the hadrons, and so they can incorporate properties such as charge or other properties of the hadrons, which you might want to incorporate. And then you have UV detectors which kind of reach in and actually measure the individual quarks and gluons. And you can derive, and I've written it very schematically, but just like you would for local operators, you can actually have some matching equation between your kind of nice, in this case, infrared detectors and your UV detectors over here. And so the very nice aspect of this is that we can actually do this kind of very or systematically, and this really enables precision theoretical calculations for measurements using these tracking detectors. And so in particular, this enables us to kind of unlock this data, which was kind of measured from this inner tracker of these old experiments, which was never used and was just kind of sitting there for 30 years. And so just to kind of illustrate the improvement that this actually leads to, so this is a kind of map of the celestial sphere where these two dots are meant to represent the two kind of energy correlator detectors. And so over here is the resolution which was achieved in this first Pluto experiment. Here is the resolution which was achieved in these kind of Aleph and LEP measurements in the 90s. And this is the resolution that we can now achieve using this inner tracking detector. And so this really kind of transforms what we're able to actually measure. And this enables us to measure for the first time at an actual sub-confinement resolution. And so we'll be able to see kind of interesting QCD confinement phenomena using these measurements. OK. And so using that, what we wanted to do is to use this amazing data set to actually measure these energy correlator distributions all the way from this kind of partonic regime to this hadronic regime. And so we recently had this paper with a large number of excellent experimentalists as well as theorists. And so we were very happy that we were able to kind of disprove this and actually use this LEP data and publish a kind of new paper using their original data. And so before I show you the actual result for the distribution in QCD, I wanted to first show what this looks like in certain toy theories to kind of orient yourself to how this, or so to kind of give some intuition for how this observable behaves. And as I said, the kind of nice thing about this observable is you can compute it in a variety of different theories and compare it to QCD. And so the simplest theory which one can consider is just a completely free theory. And so to make it have something interesting, what you can consider is some large charge operator. So for example, just phi to the k or some heavy operator which you put in. And so here there's really no interactions. So this produces just a kind of whole bunch of particles coming out like this. And so you can compute this, and it's just an exercise in phase space saddle point integration because there's no interactions. And so what you get is that the distribution is uniform, which I've shown in this kind of data in this dashed purple line, plus some corrections which go like 1 over k. And so it'll be important when in the future plots to kind of associate this kind of flat behavior with this kind of uniform distribution of kind of non-interacting things. So the second example, which is much more interesting, is in a conformal gauge theory at kind of weakish coupling. And so this is something someone cannot do it non-perturbatively, but there's kind of limits of the correlator which we can understand exactly in the case of a conformal gauge theory. And for this, it will really be important. There's a gauge theory, and this is, of course, because we have our eyes on QCD. This is why we're using this gauge theory. And so what I want to just kind of do is to step through how the kind of kinematic limits, in particular this collinear limit and this back-to-back limit, kind of cleanly probe the properties of the kind of low and high spin limits of operators in this theory. So the first limit, which can be understood exactly, is this kind of small angle limit as I bring the two detectors on top of each other. And so this is governed by a particular operator product expansion. The details of this don't matter too much, but what it gives rise to is a kind of power law behavior governed by certain anomalous dimensions in your theory. And so if you're at weakish coupling, this will in particular be dominated by the twist 2 operators with spin 3. And so what this actually, or the way of thinking about this, is this operator product expansion gives some kind of leading operator or detector operator. And what I'm essentially doing is isolating that particular state, so this time this twist 2 spin 3 operator, and I'm essentially kind of isolating that state, or that state kind of dominates my measurement and leads to this very nice power law behavior shown here. And so at weak coupling, this anomalous dimension is very small, and so this behaves almost kind of like a single particle state. In the opposite limit, in a gauge theory, I have something much more interesting which happens, which is as I try to bring these two detectors apart, I have some kind of long-range conserved gauge flux, which has a very interesting or kind of characteristic behavior in gauge theories, in particular when it has a logarithmic growth of the anomalous dimensions as a function of spin. And so if you work out what is actually probed in this, and so I won't go through it in detail, but at a value, or you're essentially probing a value of the spin that kind of goes like 1 over 1 minus z. So as you go into this back-to-back limit, you're probing the kind of very high spin behavior, or this kind of Wilson loop or Aldane-Maldacena flux tube behavior. And so this leads to a much more complicated behavior, which really strongly deviates from the kind of single power law shown over here, and in particular completely asymptotes to a flat behavior. And so this will be very important later on when understanding the effects of confinement, which will be very different in these two particular limits. Okay, so now that I've kind of gone through those two examples, I can show you the actual data for the real world. And so what's shown is in purple is the measurement using this kind of amazing high-resolution detectors, which I showed before, and then in blue is our calculation. And so I'll step through the different pieces of this plot in the coming slides, but just to kind of emphasize it in a little bit of, or to give a kind of high-level overview. So as I mentioned, in the middle, we're really probing the dynamics of the theory at some very high energy. So in particular, this is set by the Z resonance. So this is really described by interacting quarks and gluons, and we can compute it in perturbation theory. And then as I go either direction, I have some kind of flow to the IR, where ultimately on either side I have some kind of free hadrons in my detector, which you can really see asymptote to this flat scaling behavior of non-interacting hadrons. And so one kind of remarkable thing about the resolution of this measurement is you can really see that you essentially go for an order of magnitude below the confinement transition. And so you can really see that in the IR, you have really like non-interacting hadrons. And then so at intermediate scales, you go through either the scaling behavior of these Wilson loops, which then confine, or you go through this light ray operator product expansion, which then again goes into hadrons. And so again, you'll see from the theory calculation that we completely lose control as we go to either of these regimes. But the nice thing is that we really understand the phenomena that's going there. And so we hope that we can use this to draw nice conclusions about the behavior in real-world QCD. And so now what I want to do is just kind of step through the different pieces of this calculation in a little bit more detail. So as I mentioned, so in the middle of the distribution, you have no kind of nice operator product expansion or no single state that dominates. And so the best we can do is perturbation theory. But we are actually quite good at perturbation theory. And so in particular, we can do it to quite high orders. So we're in particular going up to third order in the strong coupling constant. So we're including quite high states with many gluons. And so you can see that if you do that calculation, we actually get beautiful agreement between this calculation performed on partons and what we see in the real world experiment. And so this really kind of shows that in this intermediate or in the bulk region, we really have kind of these partons in the UV. So now what we can do is to start moving more towards the large angle side where we generate this kind of flux between the two detectors. And so in this limit, we're really dominated by this kind of leading Wilson loop contribution, or this leading kind of flux tube contribution. And so one very nice thing about this is because it kind of projects us down to this single contribution, we can compute this to extraordinarily good accuracy. And so this is a very sensitive probe of this log J growth of the anomalous dimensions in QCD. And so in particular, for the cusp anomalous dimension, which is really what governs this, we can actually compute this to 5-loop order in QCD. So this is really kind of using, or is an illustration of the absolute kind of state-of-the-art of what is computable in perturbation theory. And you can see that what we get out is this kind of beautiful agreement at almost the percent level. So it's about kind of 2% or 1% between what we compute in, or what we compute and the data. And so this is kind of a really nice illustration of these advances in perturbative techniques. And so it doesn't matter the exact details of this, but this is just to show you that if you use kind of lower order calculations, and so the actual original calculation is even lower than what's shown on here, is that you really get large, very large uncertainties, and you really need these kind of very high order results to actually get this nice agreement. And so one thing you can ask, which is actually related to your question showing earlier, is once you have this level of agreement, can you detect kind of small imprints of confinement already in this regime? And so as you said, so in real world QCD, the particles are massless and the hadrons are massive and do not make it out to asymptotic infinity. And so instead, they have some kind of velocity which is going along. And so one way of thinking what this does is in this original expression which I showed you, if you really had massive particles, you excite kind of arbitrarily high spins. If I put a cutoff on the velocity of these distributions, or the velocity of these hadrons, essentially what happens is I truncate the maximal value of spin in this, and this actually leads to a small deviation which is computable, or its functional form is computable in QCD. And so you can think of this as a kind of large spin expansion about the massless case, and it's a little bit hard to see here, but this actually leads to about a 10% deviation in real-world QCD. And so to actually, once we have things at the level of 1%, you actually really need to incorporate this understanding. So it really shows that you have control over kind of real-world QCD at the few percent level, and kind of really motivates an improved understanding of these effects. Okay, so we can also now go to this collinear limit where we bring the two detectors together. And so as I said, in this limit, it's governed by this light ray operator product expansion. And so in this case, what you're probing is not this kind of high spin limit, but it's instead or kind of a limit at some generic spin, some particular spin 3. And so this is harder to compute in perturbation theory, and less is known about kind of the generic spin values as opposed to the high spin limit. And so unfortunately, in this case, we're only able to do, although it's still quite good, but a 3-loop calculation. And you can see that it still agrees very nicely with the kind of data, but you're getting kind of slightly larger, so the kind of, say, 5% or so level, instead of this amazing behavior that we have in this high spin limit. And so that's quite nice. But of course, so this kind of shows, in some sense, that we have control over these objects in perturbation theory. But one thing which one would like to do once one has control over perturbation theory is see what happens kind of to these observables non-perturbably, or what is the actual effects of of contributions that we do not understand. And so as I mentioned, one of the nice features of this is we're now able to measure below the confinement scale. And so this is just to kind of highlight in these earlier data, which are shown, for example, in the blue, we kind of lose control, whereas now we're really able to measure all the way to extremely small angles, both in the back-to-back and the collinear limit. And so in these regimes, we won't be able to compute what happens, but we can kind of push our calculations and see what actually happens non-perturbably in QCD. And so in both of these limits, what I'll do is I'll kind of compare what happens in a kind of conformal gauge theory on this side, and then what happens in the real world on this side. And so remember, in these plots, what I'm comparing is this small angle regime over here. And so in a conformal theory, I just have this beautiful power law, which kind of goes on forever. In real-world QCD, what happens is, remember that as I go to smaller and smaller angles, I'm probing lower and lower scales. And so first what happens is my coupling begins to increase, and then ultimately I just confine, and I have some scale, which kind of breaks that nice power law scaling, and then I transition to having just this scaling of essentially free hadrons which are not interacting. And so you can really kind of see by eye this nice transition occurring of confinement. And you can also see that in our calculations, we just lose control of what's happening. But this is really kind of showing that the hope is that we can gain insight from these very precise measurements of this confinement transition to actually learn something quantitative about the transition of, in this case, these kind of light ray states into hadrons in the detector. So we can also do this in this back-to-back limit. So again, here one should be comparing this kind of limit in the case of a conformal gauge theory, and this is this equivalent in the real world QCD. And so the behavior of confinement in this limit is very different, because already in perturbation theory, I'm able to kind of form this flux tube, which even in the conformal case turns me over like this. And so it's important to emphasize that this turnover in the back-to-back limit is not set by the scale of confinement, so it's not actually set by the mass gap, but it's just a property of the coupling of the theory. And so in particular, what happens in this limit is I start to lose control of the calculation, but it really does already turn over. And then you kind of have the kind of breaking of the string, which just kind of continues into this uniform behavior going out here. And so again, you now have a kind of very nice measurement of the kind of confinement in the large spin regime of this energy correlator observable. OK, so there's two additional comments which I wanted to make about this back-to-back limit. So the first is actually a very nice overlap with certain lattice results of Fiala, who's part of this collaboration. And so one neat thing is that in this back-to-back limit, in the real world, so instead of evaluating this cusp anomalous dimension, which I mentioned, at some fixed value of the coupling, as I said, as you're probing different values of the coupling, you're actually kind of sweeping over the value of this anomalous dimension at which you're probing it. And so really what you're actually measuring is some kind of integral over this, which depends on the scale. And so in real-world QCD, this integral can go low enough that it becomes non-perturbative. And so one kind of very nice result or advance recently on the lattice side is it's become possible to compute these integrals of the cusp anomalous dimension or certain properties of these Wilson loops non-perturbatively on the lattice. And so it's a little bit hard to see in this calculation because it's covered nicely by the lattice results. But this kind of black thing here, which is exactly under this, and then kind of diverges here, is actually the calculation of this object in perturbation theory. And so you can see that we actually agree nicely and really extrapolate smoothly onto the values of the lattice. And so it diverges at about 0.5 Fermi. But so we're actually able to incorporate these lattice calculations into our calculation, which allows us to extend the regime of our calculations even further, though ultimately it does fully kind of break down. And so I think it'd be very interesting to kind of further sharpen this connection between the different pictures, namely from the lattice, perturbation theory, and these kind of effective field theories for the QCD flux too. So the other kind of very nice thing, which is more kind of suggestive and which is, again, where we really lose control, is what we believe to happen. Yeah.
That's at large n, and the QCD is at finite n, or
yeah. So I would say at finite coupling in the conformal gauge theory, what really happens in this limit is a little bit, I would say, not fully clear. But you can think of it if you first take some weak coupling limit with n infinite, then you'll get this behavior. Really, in this limit, I would say as you go to infinite, or as you go infinitely high spin, you really have some mixing between some single and double trace things, which is not really understood. And so you can think of it as just like a large n conformal flux tube. Yeah.
But the plots on the right are for like SU3 or something like that.
Yeah, so this is for like real, yeah, so this one is for like SU3 Yang mills. Yeah. Perfect. And so then, so what is believed, so as again, we understand what happens in the infinite IR where we have these hadrons, we understand in the UV where you have this nice flux tube, and so what one believes is that at some kind of radius, which is set by like 1 over lambda QCD, this string kind of just fragments into these hadrons which propagate off to infinity. And so you can do this in simulations, and so you actually get a kind of very suggestive picture of what's happening if you look at the kind of flux of hadrons which are coming out. And you essentially kind of see, so these are the two kind of detectors, and you see this almost kind of QCD string imprinted into the detector. And so this is kind of suggestive that you're really having, that this is, or this picture, which I've drawn kind of here, can really be sharpened, and that you could actually kind of compute this using effective string theory and really provide some insights into what is happening here. And so now that you have this very high quality data, this is kind of very exciting to start actually beginning to make these connections. Okay, so again, just coming back, so when you put all those pieces together, you get this very nice view of the dynamics of QCD. So again, I think this is really just at the stage now where we understand the kind of perturbative aspects of this, and it's kind of very exciting for sharpening our understanding of these confinement phenomena, both in this kind of string breaking regime over here, as well as in this kind of collinear limit over here. And so related to your kind of question, also comparing not just with these confining theories, but also with kind of finite coupling results in conformal gauge theories, which are now becoming available thanks to the conformal bootstrap, will kind of really help us kind of elucidate the differences in these different theories, particularly in the kind of string breaking regimes over here. Okay, and so in the last little bit of the talk, what I just wanted to highlight, so this is very, very old data, and so that one can ask what one can do with kind of modern and very high energy colliders at the LHC. And so these are much messier colliders, and so it's harder to sharply draw any conclusions. But one thing which we've actually been kind of very happy with is we're able to understand and measure correlation functions of these operators just in this small angle limit, but at extremely high energy. So of course, in these very complicated collisions, you cannot measure them at generic angles, because these are really sensitive to the properties of the kind of colliding state, because it's no longer produced by some local operator. But because of this operator product expansion, in the kind of collinear limit, we're actually able to kind of make robust statements and very precisely understand these correlators. And so again, I won't go through the whole detail, but just, again, the fact that this is able to be possible is really due to huge advances in kind of modern effective field theory techniques, which really allow us to kind of combine this nice picture coming from the kind of conformal field theory side of this light ray operator product expansion through some anomalous dimensions, ultimately with underlying scattering amplitudes. And so we can really kind of combine the UV and the IR to make actually very precise predictions for what is going on in these real-world hadron collisions. And in fact, in this limit, we're actually able to match the precision of our calculations of these earlier E plus E minus calculations, because now we can do it at much, much higher energies, which is very exciting. So the first thing we can do is, again, just measure this 2-point correlation function. And so again, this is a function of the angles between these two detectors. And so instead of having this nice plot, which I showed before, we can only kind of zoom in on the collinear limit. But the very nice thing about this is you can just see by eye this kind of beautiful just scaling behavior dictated by this operator product expansion before the confinement transition. And the nice thing is that at these extremely high energies, so now this is at individual jets of about 2 TeV. So this is essentially 1,000 higher than what we were doing before. And so you can really see this beautiful scaling of these quarks and gluon states over multiple orders of magnitude. So you've really kind of zoomed in and are able to study the properties of essentially perturbative quarks and gluons before they confine. So this is kind of very satisfying to see that this really works over this wider range of energies. And so just to further emphasize the distinction between the scales compared to these very, very early plots, so notice that in this original plot, it goes from 0 to 180, whereas this plot essentially maxes out at like 10 to the minus 1 in angle. So this entire distribution is inside essentially this single data point here. And so this really emphasizes how amazing these kind of modern detectors and very high energies are, and has really kind of transformed the interaction between theory and experiment, because we're now really able to access this beautiful kind of conformal regime of QCD, and then ultimately it's kind of confining breakdown into hadrons at the end. And so one thing which is even more exciting is because you have such high energies, you can actually go much beyond and actually study the full kind of spectrum of these different operators which appear in the operator product expansion. And so one nice way of doing this is you can measure higher point correlation functions. And so if you measure, or if you kind of consider the operator product expansion between some n-point correlation function, essentially what you can work out is that it projects you onto some detector operator which has a spin n plus 1. And so if you're familiar with looking at these kind of true Fauci plots, essentially what happens is that as you measure higher and higher point correlation functions, so the 1-point function is just the stress tensor, which is conserved, and then you have the 2, 3, 4, et cetera, which just probe different spins in this true Fauci plot. And so this is very nice because it really provides a mapping between what an experimentalist can measure and the spectrum of twist 2 operators in your theory. And so you can now go out and do this experimentally. And so this is actually a plot. So here I'll always plot this ratio to the 2-point correlation function. And so it just essentially probes the kind of difference of the anomalous dimensions, or the difference of the dimensions of these operators. And you can actually measure these up to 10-point correlation functions. And this is because of the amazing high energies. And so you can really see that for each of these different, so again, this is the ratio of the n-point to the 2-point. And you can really see this kind of very nice power law behavior that you would expect here. And again, you see that these get steeper and steeper, which is just the monotonicity of the Reggie trajectories. And so for us, this is very nice because this really provides a kind of clean mapping from these very complicated experiments to something that we really understand, and we can really just measure the spectrum of these operators. And then ultimately, for each of these kind of states, we can study its hadronization properties. And so for these, again, we can do quite nice theoretical calculations up to kind of 3-loop order. But one thing which has been very satisfying is that by studying the precision scaling of these library operators, it actually now provides one of the most precise ways of measuring the value of the strong coupling constant in these hadron colliders. And so because we have this scaling under such good control, and of course this is just proportional to the coupling of your theory, you can actually, or this gives the kind of world's most precise value of the strong coupling constant from these jet substructure techniques. But it's kind of a very kind of clean way because you're really just looking at the spectrum of operators in your theory, computing it as a function of the strong coupling constant, and just kind of reading it off by eye. And so this is kind of really clarified how this is done in these complicated hadron experiments. Okay, so just to kind of start wrapping up, so 50 years of study of these kind of both on the experimental side and the theoretical side of trying to understand these correlations in energy flux have really kind of transformed this from these early kind of qualitative studies to really extremely precise predictions of over the entire range, in particular unveiling the kind of transition from the partonic degrees of freedom to the hadronic degrees of freedom, which is kind of, at least to me, a very exciting starting point now to begin asking the kind of more exciting questions. So in some sense, we've mastered a large amount of the perturbative description, and so this kind of gives us an exciting opportunity to really begin asking questions about the more interesting regimes, in particular the confining transitions, and trying to make connections with a lot of the nice theory developments made by this collaboration. And so just to conclude, so there's been a lot of recent progress in relating collider physics and field theory through these energy detectors. And so this really provides a very sharp connection between the underlying field theory and what you can measure experimentally. And so because of this, there's been a lot of experimental work where you've really been able to measure the scaling and shape dependence of these energy correlators kind of very precisely. And we now have these beautiful maps of the dynamics of QCD, which some regions we don't understand, but we understand kind of a whole bunch of limits. And so this really gives us kind of a very nice view into confining dynamics. And I think this is really an exciting opportunity to improve our understanding of the confinement phenomena in real-world QCD using advances in field theory. So thank you.